Well, hello and welcome to this Kaeser Compressors webinar. My name is Rich and I'm a Senior Manager with IHS, and I'd like to review a few housekeeping items with you before we begin. Let's take a moment to familiarize ourselves with the operation of the user interface for today's webinar. Now, the large window that you're currently viewing with the heading Kaeser Compressors presentation in the upper left, that's the primary window for today's webinar. You should be seeing the welcome slide there right now. Just to the right of that main presentation window, you'll see the speaker's bio window, and that contains background information on today's presenters. Just below that, there's a Q&A window, and at any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will then be placed in a queue for our speakers to address when we get to that Q&A session. Now, if you look to the bottom of your screen, you'll see additional buttons to enhance your webinar experience. To see what a particular button does, just hover your mouse pointer over it, and a tooltip will appear with a description of that button's function. And now to get this webinar started, here's Kaeser Compressors Marketing Services Manager, Michael Kaeser. Michael?
Good afternoon, and thank you for joining us today. Compressed air is vital for most plant operations and is quite often referred to as the fourth utility. At the same time, it is an heavy energy user. But unlike other utilities, compressed air is almost always generated on site by the user. This means each facility has the opportunity to optimize for energy savings. As you can see here, the U.S. Department of Energy estimates that half of all compressed air is wasted. This is a figure that has been proven time and time again in countless facility audits. The waste occurs in leaks, artificial demand, and inappropriate uses. The word leaks speaks for itself. Nearly every air system has leaks, and they can account for a ton of wasted energy. The average is about 25%. Some users simply accept leaks as just another operating expense and do nothing about them. Others take the step to conduct a leak detection audit, but then do nothing to fix the leaks. Artificial demand refers to the waste that's created when you make and use air at a higher pressure than necessary. There are contributing factors: intentionally oversizing, thinking it will make tools and equipment work better; providing excess pressure in the whole plant for the sake of one or a few users; compensating for pressure loss; compensating for leaks; or obsolete cascading controls in multi-unit systems that require wide pressure bands. Inappropriate uses would be anytime you're using compressed air when you could use an alternative means to achieve the same effect. For example, many times employees will use compressed air for personal cooling when it would be far more efficient to use fans. To put this in a different perspective, here's a geographic view of the portion of electricity consumed by compressed air systems in each state. The vast majority of these systems are not optimized and consequently are wasting electricity. There is great potential for power savings in the U.S. industrial base. Unfortunately, there are some significant obstacles to overcome to make optimization a reality. In the United States, most systems are initially designed with the assumption that more is better. There's little regard given to the overall system efficiency. Some buyers select efficient equipment, but often purposely oversize them. You can have the most efficient individual compressors available, but if they're not properly applied and controlled, they will waste power. Additionally, there are no considerations for possible changes in production levels. The focus tends to be on short-term metrics, such as paying the lowest price possible on the compressed air system. Mid- and long-term cost considerations are usually given little thought. This is true of new systems as well as upgrades to existing systems. If the prevalent attitudes can be overcome, there are a number of very effective ways to make improvements. Applying any of these strategies can give you noticeable energy savings. Fixing leaks alone can easily create energy improvement of 6 to 10%, and this is honestly a very conservative estimate. Choosing proper compressor controls and controlling multiple compressors from one device also offer significant savings and offer improved pressure stability. Reducing pressure drop with good maintenance practices and air treatment selection also pays back. These are very conservative and realistic numbers for improving existing systems. And if you can tap into your compressed air system as a heat source, you can get even further ahead. Now let's look at our map again. If compressed air systems were optimized using existing techniques and technology, the overall proportion of electricity consumed by compressed air systems would drop dramatically. Not only would tens of thousands of companies improve profitability, but the industrial carbon footprint would be greatly reduced. Today we'll focus on 3 strategies for energy reduction: leak detection, system optimization through compressed air audits, and heat recovery. By applying each of these, you have the chance for immediate payback as well as ongoing energy savings opportunities. Before I get into leaks, it's worth mentioning piping materials. The type of piping materials you have in your system greatly impacts both air quality and pressure drop, which wastes energy. As contaminants such as oil and dust enter the compressed air distribution system, they may build up in the pipes, especially piping that is not smooth inside. I'm sure you can see how this would prevent air from flowing freely. The goal should be to select piping material that won't promote buildup and that allows unobstructed laminar airflow. This chart gives an overview of common piping materials and their advantages and disadvantages. I'm sure it looks small in your display and it may be difficult to read. Sorry about that. But you can download a copy of the presentation later on and keep this chart as a resource. I'm not going to review all of the piping types in detail, but I will take the opportunity to caution you about using PVC piping. We see it from time to time, especially in some of the smaller systems. It's lightweight and inexpensive. However, it can be a cause for concern in terms of safety. We really do not recommend it. In fact, OSHA has ruled against it for any above-ground installation unless it is encased in a shatterproof material. If you're looking for reliable, cost-effective piping, we recommend copper or aluminum. They're both great for installation, and you will not run into trouble with buildup like some of the other piping materials. Now let's get back to leaks. As mentioned earlier, leaks can account for 25 to 30% of your compressed air energy costs. This impacts more than just your power bill. Leaks cause your system pressure to drop and your compressors to cycle. This drives up your production and maintenance costs, which in turn costs you even more money. By simply eliminating the leaks in your compressed air system, you can add 25 to 30% back into your compressed air supply. You can put the air you are already paying for back to work for you. When we talk about leaks, it's important to know that we're talking about 2 different types: intentional and unintentional. Intentional leaks are when compressed air is being used in a wasteful way. For example, timed electric traps are basically timed leaks. Unintentional leaks tend to worsen over time. They need to be periodically checked and repaired. Many people think a small leak isn't that big of a deal and that a small hole can't really be costing them all that much money. They're greatly mistaken. So just how much does a small hole in a pipe cost you every month? As you can see here, if you have one and only one 1/4-inch leak in a hose, let's say, and you are operating it at 110 psi, you're losing about $18,000 a year, and that's $1,500 a month. Now imagine how many leaks your system probably has, certainly more than one. The amount of money you are losing every month adds up. Calculating the annual cost for a leak is fairly simple. Take a look at the formula in the blue box on the slide. You simply multiply the leak rate by the efficiency rate of the compressor times the annual operating hours times the cost for electricity. In this example, a soft drink bottling company performed a leak detection audit, and they found that 200 CFM, half of their average demand, was wasted to leaks and cost them $34,000 annually. When you are considering leak detection, there are three methods: listen and feel, soapy water, and ultrasonic. The first two are the simplest. However, they require direct contact with the leak and do not give information on how large the leak is. These are the major reasons why ultrasonic leak detection is the industry standard. Ultrasonic leak detection requires special equipment, as shown in the image, but it can also give a volume level for the leak. This helps you prioritize which leaks to fix first. When you have a leak audit, there are a few points to look for. Not all service providers are the same. Make sure each leak will be tagged and clearly identified. A good audit will also provide you estimated cost and savings potential for each leak. This slide shows an example of an audit report that Kaeser provides for our leak detection audits. This is just to give you an example of the type of information and detail you can expect from an audit. After you have the audit complete, you need to have a plan in place for repairing leaks. First, repair any leaks that pose a safety hazard or would cause any kind of failure or breakdown. Second, going with the 80-20 rule, fix the largest leaks first, as soon as possible. This will give you immediate payback. Third, the next larger leaks. These still account for a significant loss, but not as much as the top 20% typically do. But you have to consider how many of these you may have. Fourth, address the smaller leaks as time permits. Monitor these minor leaks and repair them immediately if they worsen. Finally, keep in mind that when it comes to leak detection, it is not a one-and-done kind of task. Make leak detection part of your annual maintenance to keep leaks under control. And now Neil Meltretter, Kaeser's System Design Manager, is going to speak with you on using compressed air audits to identify areas for energy savings potential.
Thanks, Michael. Many air system owners don't have a clear picture of how their system operates or how much energy it actually consumes. Compressed air audits are a great way to baseline the system and visualize what's happening before you try to make improvements or add compressors to accommodate plant expansions. An audit can help you prioritize your actions as well. Knowing how much energy you use to compress air should be a primary goal. An audit will help you do this and help you identify components of that cost, such as leaks and unproductive uses. The data collected can be used to determine the optimal mix of compressed air equipment for the existing need or future expansion. An air audit from a competent compressed air professional is a great first step in determining compressed air efficiency, along with a leak detection audit and evaluation of each compressed air user will improve overall system performance. Audits can vary widely in scope, quality, and price, from free compressor measurements to comprehensive supply and demand-side audits. The comprehensive audits are generally conducted by independent professionals and encompass extensive testing in both the compressor room and within the facility. These audits typically include detailed evaluation of each compressed air user. These can be very valuable, and they typically cost tens of thousands of dollars. Of course, many compressor suppliers offer audits as well. Some are useful and some are unreliable. Here are some things to expect in any worthwhile compressed air audit. Whoever does your audit should view your compressed air system and the plant equipment it feeds, along with the piping network. They should ask you for or make a system drawing that they review with you to confirm its accuracy, which would include a block diagram of the compressor room, specifically compressors, dryers, filters, receivers, and piping. It's important to discuss the goals of the audit, the desired outcome of the audit, and possible system changes expected, whether that be plant expansion, changes to air quality required, or something else. This will help determine the best measurement plan. Consider that some poorly performing compressed air systems can be improved immediately. If the compressed air auditor determines that piping within the compressor room is just too small to accommodate the prevailing demand, or the lack of a master controller is constantly requiring multiple compressors to load when only one is necessary, these items can be addressed prior to completing an audit. However, typically, upper management requires details on savings potentials, and in those cases, an air audit should be completed first to provide such savings potentials, and subsequent audits be completed as necessary to show those improvements in the system. Data should be collected for a complete plant operating cycle, since production and operations vary during the week. Usually 7 to 10 days is enough. Production schedules can vary, and that's why it's best to confirm that the operating period that's going to be measured will be indicative of typical plant operation. If your operation varies seasonally, such as agricultural processing, then multiple audits at various times of the year may be required. The data logging devices should sample power, pressure, and flow frequently. We recommend no less than every 20 seconds to ensure we know if any compressors are rapid cycling. Many so-called audits just measure amperage and estimate power, but this is notoriously inaccurate since voltages are rarely uniform and power factor can change depending on the load of the compressor. You pay for kilowatt hours, so it's recommended to measure kilowatts at each compressor. It's also important to measure pressure at multiple locations to determine pressure drop. Recommendations include before air treatment, after air treatment, and in the distribution piping. Pressure drop across each filter dryer should be checked. In most cases, flow can be accurately calculated if the sample rate is high and accurate information on compressor output is available. Otherwise, you should consider adding a flow meter into the study. The auditor should provide a written report that confirms how the measurements were taken and presents a visualization of flow, pressure, and power over the entire operating cycle. Again, that's usually a week. With this data, simulations can be created with alternative mixes of compressors, whether it be existing or new, or a combination of both. This will accurately project system performance after any changes are made. This can enable you to identify the equipment solution that will offer the best balance of stable pressure, reliability, and low energy consumption. There will typically be a clear winner when it comes to specific performance or efficiency. However, whether these changes have any acceptable ROI would need to be qualified. These reports should be written to facilitate decision making. An audit can help you build an energy and demand profile to help you see in black and white, or better yet, like this graphic, in color, what your system capacity is and what your production demands actually are. Let's take a look at an actual air audit chart and what it helped one customer identify about their system. First, we can see the maximum plant demand, which is the highest amount of air the system needed for the time monitoring was done. What's interesting to see is that during production times, which is about 5 o'clock to about 4 o'clock in the afternoon, the flow profile is varied. There's not a consistent requirement for the same amount of air. Now, for reference, we show the total capacity and the available capacity. This tells us that the system is actually very oversized. The total capacity of the compressor here is about 740 CFM, and the available capacity, which is the difference between the maximum plant demand and what the compressor is rated for, is about 360. There could be a significant energy savings by switching to smaller compressors, which will use considerably less energy and still produce the volume of air needed to meet the demands of the system. What this graphic doesn't show you is what control type the compressor is actually running. So if it's running in modulation control versus load-unload or variable speed, etc., there could be a very big difference in overall energy cost. A good audit will also provide you clues to non-productive loads, leaks, timed electric traps, etc. Non-productive loads can waste energy 24/7 as long as the compressors are on. In this case, the customer noted that a lot of air was being consumed after hours and on the weekends, when they were not in production. Approximately 170 CFM, 50% of the productive load, was simply being wasted. This is the equivalent of running 40 horsepower worth of compressed air all the time. This customer was spending over $20,000 in electricity with absolutely no benefit from the compressor running, not to mention the additional maintenance for this particular machine. Unfortunately, this is not uncommon and occurs in much larger systems as well. To sum up, the key conclusions we can draw from this one chart: number one, they were using only half the air they had available. Number two, peak production is under 30% of the available capacity. And number three, leaks, artificial demand, and other non-productive loads made up most of the air consumption. This is really a typical case. Knowing this information can really help you understand your system and give you an idea of how best to optimize it. Simply putting a smaller compressor in line with a better control type would certainly help. However, if nothing was done for the leaks and artificial demand and non-productive loads, you'd just be running for those times, but slightly more efficiently. Using an air audit on a regular basis can help you make sure your compressed air system is always running at its best. To finish up, I'd like to turn it over to Werner Rauer, our product manager for Rotary screw compressors. He will be presenting on turning your compressor into an energy source.
Thank you, Neil. Well, it seems like everywhere we go today, we hear and see a lot of talk about energy costs and energy savings, including compressed air system audits or assessments. So we thought it would be a good time to look at heat recovery in industrial compressed air systems. Today, we want to focus on the heat recovery possibilities and energy savings potential for the most popular type of compressor used today, the positive displacement packaged rotary screw compressor. The first law of thermodynamics and the law of the conservation of energy state that energy cannot be created or destroyed. It can only change form. So for the compressed air applications, the air that enters a compressor at atmospheric pressure and has a base level of energy content. After the compression process increases the air pressure and raises its temperature, the energy becomes available for transfer. The heat must be removed to maintain proper compressor operating temperatures and to cool the compressed air to make it suitable for planned use. The heat generated by compressed air systems can be a very good source of energy savings. 100% of the electrical energy consumed is converted into heat. Ideally, 96% of that can be recovered as heat. The balance remains in the compressed air or radiates from the compressor into the intermediate surroundings. This graph shows the percentage breakdown into heat for the total electrical power consumption that enters the rotary screw compressor. We have chosen an air-cooled, lubricated rotary screw compressor as an example because it is the most common compressor equipment found in manufacturing plants today. As you can see, about 2% each are either radiated off the compressor package and stay within the compressed air into the pipeline. Adding up the rest coming off the drive motor, fluid and aftercooler will net a total of 96% that is available for heat recovery. The amount of heat recovered using these systems will vary if the compressor is used as a trim unit with variable load. Now let's talk about some specific hot air applications. The two most popular types of compressors are electrically driven fluid-injected screw compressors and the dry running or all-free screw compressor. For both being air-cooled models, the maximum amount of heat recovery is 96% of the total electrical input power. The temperatures for the hot discharge cooling airflow range anywhere between 15 to 40 degrees Fahrenheit above the cooling air inlet temperatures. Now let's talk about some specific hot air applications. Nearly all current compressor models have cabinets that channel the airflow through the compressor, and many designs exhaust the warm air out of the top of the unit, like the one shown here. This simplifies adapting compressors for space heating to simply installing the ducting and sometimes a supplemental fan to handle duct loading and eliminate back pressure on the compressor's cooling fan. Space heating can be regulated easily using thermostatically controlled motorized louver flaps for venting and thereby maintaining consistent room temperature by making continuous adjustments to the heating airflow. This is important to ensure comfort for people within working areas. This also means that when heating is not required, the hot air can be ducted outside the building to reduce cooling costs. This heat can also be used to keep the compressor room above freezing temperatures. Typical uses include heating for warehouses or storerooms, heating for production areas and workshops, drying air for paint spraying, air curtains, and preheating combustion air to improve efficiency, for example. So for generating hot water, also several options are available. Both water-cooled versions of the fluid-injected or dry-running screw compressor can achieve pretty much the same amount of heat. However, there is a difference in the maximum water temperature that can be achieved. Dry-running compressors operate at much higher internal temperatures of more than 300 degrees Fahrenheit as compared to fluid-injected compressors that run at about 200 degrees or even below. Therefore, the dry-running screw compressors can produce greater discharge temperatures for hot water applications up to about 195 degrees Fahrenheit. But in general, very good results are achievable for both hot air and/or hot water when the primary air compressor package is a fluid-injected rotary screw type design. By tapping into the hot cooling fluid circuit, the hot water can be generated off 76% of the electric input power with maximum water temperatures up to about 160 degrees. These comparisons show where the energy comes from for producing hot water. For both water-cooled types, they are nearly the same, except for the maximum temperatures, as we just discussed. For the air-cooled fluid-injected type, up to 76% can be recovered from the hot cooling fluid. Here we show a shell and tube type heat exchanger tapping into the hot cooling fluid on the left-hand example. This example here, we are looking at a picture of several air-cooled fluid-injected screw compressors, all of which are equipped with an internal plate-type heat exchanger and controls like pump and valves that taps into the thermal energy of the cooling fluid. The highlighted red frame at the top left is indicating the exhaust air duct that carries the hot cooling air outside for the heat that was not rejected by the hot water heat recovery system. The hot air is used in cold weather periods to heat up the compressor room and the adjacent areas. The hot water lines, which are shown on the bottom right-hand side in the blue frame, along with the pumps, valves, and controls, is being used to heat up dipping baths for cleaning sheet metal prior to powder coating. Too often, the heat is simply ejected into the ambient environment through the compressor's cooling system and wasted. As we mentioned, nearly all this thermal energy can be recovered and put to useful work and significantly lower a facility's energy costs. Here are some of the many applications for using recovered energy from compressed air systems: industrial process heating, preheating boiler water, make-up air for heating, heating food and beverage products, water heating for showers, bathrooms, etc., supplemental space heating, and heat-driven chillers. Here are two examples of heat exchangers that are being used for hot water heat recovery. The plate type style on the left features a compact and efficient design and offers a cost-effective solution for a lot of applications. The shell and tube style shown on the right can also be ordered as a fail-safe design, whereas there's a double-wall tubing installed that allows for an intermediate fluid to separate the cooling fluid from the process fluid or water. A pressure monitor on that intermediate fluid chamber is monitoring for any possible leakages on either side and will provide an alarm signal in case of a breakthrough to allow shutdown of the system before the contamination occurs. The plate type heat exchangers offer a cost-effective way to capture heat from the rotary screw compressor and utilize it to heat water for diverse processes such as electroplating, chemical processing, or laundry services. The fail-safe heat exchangers provide additional protection against contamination of process water or fluids by the compressor cooling fluid. This makes them more suitable for heating applications in the food and pharmaceutical industry sectors, as well as for heating potable water. Some compressor manufacturers offer built-in heat recovery heat exchangers as an option. In some cases, they are fully integrated inside the compressor cabinet and require very little on-site engineering. I realize the text may be a little bit small for you to read, and I apologize for that, but you will be able to download these slides and read everything in detail later on. I will hit the highlights for you now. This simple return of investment sheet shows an example of a 100 horsepower air-cooled rotary screw compressor with a variable frequency drive. We chose this application to demonstrate that trim compressors like this one will have a varying amount of electrical input based on the actual compressed air demand, and therefore also a varying output of available heat for the heat recovery. In most applications, the focus for heat recovery is typically on the base load units that operate 100% loaded and therefore make consistent amounts of heat available. For this plant, we are using gas at a cost of $1 per therm and a boiler efficiency of 82% to generate hot water. For this compressor, 72% of the total electrical input power of approximately 82 kW is being considered for an upgrade to an externally mounted heat recovery option at a cost of $28.27 for just the compressor modification. The total electrical power cost of operating the compressor is about $42,640 at 10 cents per kW hour. As you can see, the available amount of energy savings due to the heat recovery varies with the actual load condition of the compressor, which we show here at 40, 60, and 80%. This results in a return of investment from 7 down to 4 months or better based on the demand for compressed air from this compressor. For a base load compressor operating at 100% load, it would look even better. As mentioned earlier, the actual energy type and cost currently being used for generating heat is very important. A lot of times people just talk about the possible savings of electricity in terms of operating the compressor, but they do not calculate the true cost savings for the actual plant application. As a side note, the listing at the lower right-hand side is in order of energy cost, with electricity being the highest and natural gas or coal the lowest. As they say, your actual mileage may vary, but this example is on the conservative side. Here are some steps as a roadmap to heat recovery. Step 1. Collect data to realize the potential. You make an analysis of the heat medium, the temperature levels and differentials, the volume flow rate, the specific heat capacity of your media, the hours of operation, the continuity of the heat source, and structural conditions. Step 2. Identify suitable uses like space heating, process heating, water heating, drying, etc. Step 3. Determine available heat energy. You look at the compressor parameters, the measured loading times of the compressors, the working hours per year, and the type, usage, and cost of heating energy. Step 4. Now you match the heat source with the heat use or storage. You analyze the local conditions, the period of time the heat is being used or needed, the choice of components, the overall layout, and the calculation of profitability or return of investment. Again, if this is difficult to read, I apologize. Let me just highlight a few key items on this list. You can always read it fully when you download the slides. Let's focus on some of these key items here. Consult the manufacturer for help. The energy saving potentials are real and they're there. Consider other compressed air system improvements or at least an audit. Plenty of resources are on the internet at the Compressed Air and Gas Institute, KGI, the Compressed Air Challenge, and or the Department of Energy. And I thank you very much for your time. And now I think Michael has additional resources he would like to share with you.
Thank you, Werner. Here are some links to additional compressed air resources, including white papers, information on compressed air audits, leak detection, as well as our company blog. And now, with the time left, we'd like to take some questions.
Okay, Michael, Neil, and Werner, thank you all for your time and your expertise today. Now, we do have some questions that have come in from our attendees, so let's get started with those. But first, as a reminder to all our attendees, if we don't get to your question, don't worry. We'll have an answer for you within 24 hours. The complete Q&A transcript, including answers we did not have time for, will be sent to all of our registered attendees and will be posted with the webinar when it goes into the on-demand mode. Now on to our first question. Neil, this question looks like it's for you. How often do I need to do a compressed air audit on my system?
Sure, it's a great question. In general, it really depends on the system itself. Larger industrial ones, I'd say definitely annually. Anytime you're considering new compressed air equipment is also a good idea. If you have a specific new CNC that's going in the facility and you want to know, hey, how much air do I have in the system additionally? So if you do an audit, that's the perfect way to really see how much air is available for this new use and to see if additional purchase of equipment is required. Also, if you're noticing any problems with the system, such as inconsistent pressure or higher energy costs, that's a good time to do an audit. The audit can help you find the reasons for those specific problems and help you identify solutions. In general, technologies change over time, whether it be with new master controllers, with new controls for compressors themselves. So if you notice that your system is aging, now might be a good time to do an audit. Thanks. Good question.
Okay, thanks, Neil. Here's another question for you. Where can I find a reputable compressed air auditor?
Sure. There are a lot of auditors out there, and some are more reputable than others. What you need to decide is what type of audit that you want. Is it a supply side or a demand side or both? Remember when we talked about this before, if you're doing both supply and demand, typically this is a very comprehensive audit and you're going to be spending tens of thousands of dollars to do it. So you have to figure out, number one, what are the goals of the audit? And that's going to help you decide on which compressed air auditor you might want to talk to. The best advice I can get you, or tell you, is you're going to get what you pay for. Some auditors or some audits may be cheaper than others, and that cheaper option may not give you what you want. What are those goals? Some audits only measure amperage, then calculate power, and then calculate flow. So, if you have a set of charts, you have a sample report from the auditor that you're talking to, that'll help you understand what it is they're going to do, what's the measurement plan, how is that measurement plan going to help you meet the goals of your audit. Kaeser also does supply-side audits, focusing on the compressed air equipment and also the distribution network. So if you're interested, you can visit www.kaeser.com/ADA for more information about our audit program. Thank you. Good question.
Okay, thanks, Neil. Michael, this question looks like it's for you. How often should I do leak detection?
Yes, I would say generally annually, but it depends on the size of the system. Small shops where you routinely see all the piping and might actually hear leaks may not need a formal leak audit annually, but a larger plant should have one annually. Here's a helpful tip. If you're planning a compressed air audit, do the leak study first and fix the leaks. This will give you a more accurate demand profile to work from in your audit. Larger systems, after doing an initial leak audit, you'll want to follow up to make sure leaks have been corrected and to monitor the smaller leaks.
Thank you, Michael. Here's another question for you. Can I do the leak detection myself, or should I hire someone?
Well, you really have some options here. We've got customers who hire it out, and we have some who buy the equipment and do it themselves, or borrow the equipment and do it themselves. You just have to consider that it takes some time and experience to develop the experience and get a feel for doing it. And there's the cost of the equipment and the time of the labor. If you have a large plant or multiple plants and you have technicians or personnel available to be trained and spend time on it, then it might be worth it. But if you don't, then it might be more cost effective to just hire it out.
And staying with you, Michael, what is the best way to start optimizing my compressed air system?
Sure. There are many avenues for optimizing, but you need to measure before you manage. A compressed air audit is the way to gather this data. Make sure you have a thorough understanding of your system and process, and the audit gives you that. But before starting with any project, you should start by getting buy-in from key decision makers on getting the data and the willingness to act on it. Without this buy-in, you may be setting yourself up to fail.
Okay, great. Werner, I think this next question is for you. Can I add heat recovery to my current system?
The short answer is yes. Some compressor manufacturers offer retrofit kit options that are great for existing systems, but keep in mind, check your current equipment. If it's outdated or inefficient, it won't get you as good as a return of investment. Do the math. In some cases, you might be better to go with new equipment with an integrated heat recovery option.
Thank you very much, Werner, for that answer. And Michael, it looks like we're back to you for this question. How often should we inspect our piping for buildup?
Well, a key predictive maintenance plan might include an annual inspection of the piping system at key points, but what you really want to look for are indications that there's a problem. So one indication might be increased frequency in changing your filter elements. You've got more rust or dirt or contaminants in your filters. Or you're not getting good flow all the way to your points of use. If you have increased pressure drop down to your points of use, that could indicate a problem. This assumes, though, that you haven't added more flow to the system. If you've added compressors or added larger compressors and added more flow, you might have pressure drop just due to air friction.
Great, thanks, Michael. And it looks like we have time for one more question. Werner, this one would be for you. How big does my system have to be to get a good ROI when using heat recovery?
The size of the system certainly is a key factor, but not the only factor. You should also consider the efficiency of the equipment. Older equipment won't give you a quick return of investment. The type of energy you're using, the cost of the energy which varies by geographic location and the size of your factory. You really need to do the math. If you aren't sure, consult a system expert for help running the numbers.
Okay, gentlemen, we're going to have to wrap up this webinar right there. Michael, Neil, and Werner, thank you so much for spending some time with all of us today and sharing such great information. And thanks to all of our audience members for being part of this webinar event. Now, as a sign of our appreciation, all attendees that register, attend, and complete the survey have a chance to win a $100 Amazon gift card. We'd like to let you know that you'll be receiving an email from us with a link to the on-demand version of this presentation, a PDF of this PowerPoint, and an FAQ document, along with the Q&A transcript. Lastly, please take a moment to complete our survey that will appear on your screen at the end of this webinar, and you'll have a chance to win that $100 Amazon gift card. Again, thanks for taking the time to join us for today's webinar. Take care, and we'll talk to you soon.